Massive stone structures have survived for thousands of years without a single steel beam. They stand as a silent challenge to our modern understanding of engineering. How did ancient builders achieve such structural perfection using only stone, wood, and earth? By the end of this journey, you will possess the lost principles that could revolutionize how we build for the future. We will uncover how stones were cut to fit with impossible precision, and how entire buildings were designed to dance with earthquakes. What forgotten wisdom do these ancient stones hold for our world today? A lone stonemason in ancient Egypt runs his hands over a block of limestone. His choice is not random. It is guided by a deep, generational understanding of the stone's soul, its strengths, and its hidden weaknesses. This intimate knowledge of material is where all structural perfection begins. Across the ancient world, from Rome to the Andes, builders worked with a shared set of unspoken rules. They mastered three invisible forces: gravity, compression, and the inherent strength of their local stone and timber. The Roman architect Vitruvius later codified this wisdom into three principles: fermeters, utiliters, and venusters. At its core, fermeters, or durability, was paramount. It was achieved by ensuring that every single stone knew its place in a grand choreography of weight. Builders understood load distribution not with complex mathematics, but with an intuitive feel for how forces travel. They knew that the weight of an entire wall, even a massive pyramid, must be channeled downward safely into a stable foundation and ultimately into the waiting earth. This is why the first and most critical step was always the foundation, a meticulously prepared base that would not settle or shift. Builders always used what the land provided: local granite, sandstone, or volcanic rock, because they understood its properties instinctively. This leads to a brilliant example: the Incan walls of Sacsayhuamán. These walls are a puzzle of irregular stones, each one uniquely shaped, yet they fit together so perfectly that not even a blade of grass can slip between them. This was not just artistic flourish, it was genius engineering. By interlocking these jagged blocks, the Incas created a structure where the center of gravity was perfectly balanced. The weight of the entire wall is distributed so evenly across every interlocking point that it becomes a single, immovable mass, shrugging off centuries of earthquakes. How did these builders develop such a profound, almost intimate, understanding of physics without a single formal equation? They learned by watching, by testing, and by listening to the stones themselves. This foundational knowledge, written not on papyrus but in the very alignment of bricks and mortar, set the stage for the most breathtaking architectural wonders the world would ever see. The sound of a wooden wedge being hammered into a seam of granite echoes across a sun-baked quarry, but the real magic happens when water is poured over the wood. As the wood swells, it generates an irresistible force, cracking the stone along a perfect, predetermined line. This was not brute force. It was a deep, almost intuitive application of material science. Ancient builders possessed an encyclopedic knowledge of their resources. They understood that granite, with its immense compressive strength, was the only choice for a foundation destined to bear thousands of tons. Softer limestone, easier to carve and shape, was reserved for intricate decorative work high on the walls. This careful selection was the first layer of their genius. The true testament to their mastery, however, lies in a material that still baffles engineers today: Roman concrete. Modern concrete can crumble in decades, but the Roman recipe, a mix of lime, volcanic ash, and rubble, has endured for millennia. When seawater seeped into their harbor walls, a chemical reaction with the volcanic ash actually caused the concrete to grow stronger, seamlessly healing tiny cracks over time. This was a self-repairing material, a technology we are only now beginning to replicate. This profound understanding extended to every element. The art of dressing stone, of carefully shaping each block with hammer and chisel, was not for visual perfection alone. It was to create a perfect fit. When two expertly dressed stones were placed together, their surfaces met so completely that the load was distributed evenly across the entire face. This eliminated points of concentrated stress, the very thing that causes modern structures to fail. Meanwhile, wood was not just a simple beam. Builders selected specific types of timber for their flexibility, creating frameworks that could sway and absorb the violent energy of an earthquake, protecting the rigid stone walls they supported. They even developed methods to treat wood, charring it or soaking it in salt to resist rot and insects. Nowhere is this holistic material mastery more evident than in the pyramids of Giza. Millions of limestone blocks, each one precisely cut and dressed, were lifted into place. The builders knew the exact properties of that local limestone, how much weight it could bear, and how to position each block so that the entire structure acted as a single, unified mass, channeling its unimaginable weight down into the stable desert bedrock. This was not just construction. It was a form of alchemy, transforming simple stone, wood, and earth into monuments for the ages. The question is, how did they then assemble these perfect materials into forms that could defy the earth itself? The final piece of stone slips into the arch, a wedge-shaped block at its crown. With this keystone in place, the entire structure transforms. The unstable pile of individual stones becomes a single, unshakable entity, capable of holding up immense weight for millennia. This is the principle of gravitational equilibrium in action, a secret the Romans perfected. They understood that an arch does not simply hold weight up, it elegantly redirects it. The force of gravity pushing down on the arch is converted into a powerful outward thrust along its curved sides. To contain this energy, Roman builders employed massive abutments or thick walls, essentially giant bookends that pushed back, locking the arch in a perfect state of balance. This same principle was elevated to its most breathtaking form in the dome. A dome is essentially an arch rotated around its center, creating a continuous compressive ring that distributes weight evenly in all directions. No single point bears too much stress, allowing for vast, open spaces below. The ultimate expression of this is the Hagia Sophia in Istanbul. Its colossal dome appears to float, weightless, above the cavernous interior. This illusion of lightness is the direct result of an almost perfect gravitational equilibrium. The dome's weight is channeled down through a series of smaller half-domes and finally into massive piers, a cascading flow of force that was calculated not with computers, but with generations of accumulated experience. How could a builder, using only a rope and a plumb line, possibly calculate the exact curvature needed to keep such a massive structure from collapsing under its own weight? They learned to read the language of forces, to see the invisible lines of compression and tension in their mind's eye. They built a legacy not of stone and mortar, but of perfect balance. And this mastery of balance would soon be tested by the most unpredictable force of all, the trembling earth. A single rope, a few wooden stakes, and a patch of level sand were the only tools an ancient architect needed to lay out a perfect right angle. They would create a loop of rope with 13 equally spaced knots, forming 12 equal segments. Stretching this rope to form a triangle with sides of 3, 4, and 5 segments, they conjured a perfect right angle from a simple loop of cord. This was the practical application of the Pythagorean theorem, centuries before Pythagoras himself was born. These simple tools unlocked a universe of geometric precision, a language of shapes and ratios that builders believed echoed the very order of the cosmos. For them, mathematics was not just a tool for measurement, it was a spiritual bridge between the human world and the divine. The Greek philosopher Plato wrote that geometry draws the soul toward truth, a sentiment shared by cultures across the ancient world. They saw in perfect circles and harmonious triangles a reflection of universal balance, and they sought to embed this celestial harmony into their temples and monuments. This philosophy gave rise to systems like the Egyptian Seat, a precise slope for pyramid construction, and the Greek golden ratio, a proportion of approximately 1.618 to 1, found repeatedly in nature. These were not abstract ideas, they were the practical blueprints for beauty and stability. An architect would use these fixed ratios to determine everything, from the distance between columns to the precise height of a ceiling. This created a building that was perfectly scalable, where every part was in a harmonious relationship with the whole. The result was a structure that felt inherently correct, both to the eye and to the underlying physics. The Pantheon in Athens is the ultimate testament to this practice. Its designers knew that straight lines can appear to sag to the human eye, and that perfect mathematical proportions can look unbalanced. So they engineered a masterpiece of optical illusions. The platform curves almost imperceptibly upward in the center, and the columns lean slightly inward. Every single line was intentionally curved or angled to create the perception of perfect straightness and harmony. Why would any culture invest such immense effort into these subtle, invisible refinements? Because they were not just building structures, they were composing a symphony in stone. A building born from these sacred proportions achieved a rare synthesis, where its visual grace was a direct consequence of its structural integrity. The mathematical harmony distributed stresses elegantly, making the entire form inherently stable. This deep-seated belief in a connected universe, where cosmic order could be expressed through mortar and stone, compelled them to build in a way that resonated with the heavens themselves. The stones of Machu Picchu fit so perfectly that they seem to have grown together. This is the art of dry stone walling, a construction method that uses no mortar at all. Stability emerges entirely from friction and the masterful interlocking of shapes. Andean masons approached each stone not as a block to be forced, but as a unique piece of a three-dimensional puzzle. They possessed an incredible understanding of stone morphology, seeing the hidden potential in every irregularity. A builder would carefully carve a subtle concavity into one stone, matching it perfectly to a convexity on its neighbor. When joined, these stones did not simply sit next to each other, they actively gripped one another. This created countless tiny contact points, distributing the load of the wall evenly across a vast interlocking network. The choice of polygonal stones with their many angles was a deliberate act of genius. Unlike uniform rectangular blocks that can form straight lines of weakness, these jigsaw-like shapes create a wall without a single continuous seam. The entire structure becomes a cohesive mass, far stronger than the sum of its parts. Builders further reinforced this stability by strategically placing the largest, most massive stones at the base. This lowered the wall's center of gravity, anchoring the entire assembly firmly against the earth. Modern engineers studying these walls have made a remarkable discovery. During an earthquake, the stones are designed to dance. They can shift and rotate slightly, absorbing and dissipating the violent seismic energy. Then, as the shaking subsides, gravity and the precise interlocking shapes guide every stone back to its original position. This property, known as dynamic stability, is a principle we strive for in modern earthquake-resistant design. What does this ancient art teach us about building for resilience? It shows that true strength is not about rigidity, but about intelligent flexibility. It is a system designed to move, to adapt, and to endure. This profound understanding of balance through assembly leads us to an even greater mystery: how entire cities were engineered to ride the waves of the earth itself. A Roman aqueduct strides across a valley, its rhythm of arches a silent symphony of pure physics. Each arch is not merely a beautiful shape, it is an engine for channeling immense weight. The genius of the arch lies in its transformation of a crushing downward force into a powerful outward push. This thrust is the arch's secret, a lateral energy that must be met with equal resistance. This is why you see such massive, thick walls or sturdy piers flanking ancient arched structures. They are the essential bookends that contain this force, holding the entire system in a state of perfect, locked balance. Before the Romans, cultures like the Etruscans had already unlocked this principle, but it was Roman ambition that scaled it to breathtaking proportions. They did not stop at a single arch. They extended the principle into the vault, which is essentially an arch stretched through space to form a ceiling or a tunnel. This simple yet profound evolution allowed them to roof over vast areas, creating the grand public spaces that defined their civilization. The structural implications of the arch's shape were further explored by later builders. The rounded Roman arch creates a steady, uniform outward thrust along its entire curve, but centuries later, Gothic architects introduced the pointed arch. This innovation did more than just change the aesthetic, it fundamentally altered the physics. The pointed arch directs more of the weight vertically downward, reducing the sideways thrust and allowing for taller, more slender walls filled with the stained glass that defines Gothic cathedrals. The ultimate expression of this vaulting mastery is found in the Roman Pantheon. Its magnificent dome is not a solid shell of heavy stone, but a masterpiece of engineered lightness. The builders used a coffered design, carving recessed squares into the interior surface. This was not merely decorative, it was a brilliant weight-saving measure, removing tons of unnecessary material from the highest, most critical points without compromising the dome's structural integrity. This immense concrete dome, still the world's largest of its kind, channels its phenomenal weight down into a continuously thickening wall, a perfect drum of compressed strength. How did these arches and vaults change the very fabric of ancient society? They enabled the creation of vast, column-free interiors, spaces like the sprawling public baths and the grand basilicas where citizens gathered. These were not just buildings, they were engineered environments that shaped daily life, all made possible by a profound understanding of how to make stone carry its own weight in the most elegant way possible. How did human hands move mountains? The towering stones of Stonehenge stand as a silent question, each massive block a testament to a mystery that spans the globe. From the windswept plains of England to the remote island of Rapa Nui, ancient societies repeatedly accomplished the impossible, lifting and placing stones that weigh as much as 50 tons. This was not a story of magic, but of a profound, shared understanding of leverage and mass. The real secret was not just the application of force, but the orchestration of it. Moving a single megalith required a symphony of coordinated effort. Archaeologists studying sites like the colossal Baalbek trilithon suggest the use of simple, brilliant technologies. Wooden sledges greased with animal fat could slide a giant stone across the landscape. Teams of workers would then place log rollers underneath, constantly moving the rear logs to the front, creating a continuous path. To lift a stone upright, they likely constructed massive earthen ramps, dragging the stone to the brink of its foundation before carefully lowering it into place. Other methods involved the clever use of counterweights and levers, using the stone's own mass against it to pivot it into a standing position with painstaking control. The final act of precision, positioning the massive lintels atop the uprights at Stonehenge, would have required another ramp or a sophisticated system of levers and packing, lifting one end at a time until it slotted perfectly into place. But the engineering is only half the story. Why go to such extraordinary lengths? Many of these sites, including Stonehenge, are precisely aligned with the sun and stars, marking solstices and celestial events. They were cosmic clocks, calendars, and temples all in one. This points to a powerful cultural drive, a collective need to build something that would echo through the ages. This same impulse is carved into the volcanic rock of Easter Island. The moai, those brooding monolithic statues, were not simply erected where they were found. They were carved at an inland quarry and then transported miles across the island, likely walked upright in a rocking motion by teams using ropes. This Herculean effort speaks to a society united by a common purpose, a shared belief system that made such monumental labor not just possible but essential. What drove these cultures to pour generations of effort into stone? It reveals a deep-seated human desire to reach beyond the everyday, to create a permanent mark on the world through sheer collective ingenuity. These stones are not just monuments, they are the physical manifestation of a community's identity and its connection to the cosmos. A devastating earthquake can reduce a modern city to rubble in moments. Yet in that same tremor, ancient structures in the world's most active seismic zones often stand firm, their survival a silent lesson in resilience. These builders did not fight the Earth's fury, they designed their creations to dance with it. This was an intuitive form of earthquake engineering, perfected centuries before we had a name for it. They understood that rigid structures shatter, while flexible ones can sway and survive. In Ottoman Turkey, for instance, architects built mosques with flexible iron clamps that connected massive stone blocks. These metal links acted like ligaments, allowing the masonry to flex slightly during a quake instead of cracking. They also integrated horizontal wooden beams directly into the stone walls. These timbers did not just hold things together, they acted as shock absorbers, dissipating the violent energy as the walls moved. This principle of allowing controlled movement is at the heart of modern base isolation, where a building is essentially decoupled from the shaking ground. Ancient builders achieved a similar effect with sliding joints in their masonry, surfaces that were polished or designed to allow for tiny, non-destructive shifts. Two other design choices were critical for this seismic resilience. The first was a deliberately low center of gravity. By making structures wider at the base and tapering them upward, builders anchored them firmly against the ground, preventing them from toppling over. The second was the use of lightweight roofing materials. A heavy roof creates immense inertial forces during shaking, acting like a pendulum that can tear a building apart from the inside. By using lighter materials, they dramatically reduced this destructive potential. Nowhere is this ancient wisdom more elegantly expressed than in the pagodas of Japan. These multi-tiered towers are designed around a central pillar known as the Shinbashira. This massive post does not support the building in the way a modern column would. Instead, it hangs loosely from the top or is set on a base, acting as a giant pendulum. When an earthquake strikes, the flexible floors of the pagoda sway back and forth, while the heavy Shinbashira swings in the opposite direction. This counter-motion absorbs the seismic energy, dampening the violent shaking and allowing the entire structure to oscillate safely. It is a brilliant, passive damping system carved from a single tree. How can these time-tested techniques inform our own quest for safety? They teach us that the most robust structures are not the stiffest, but those designed with an innate capacity to move, to absorb, and to endure. This ancient legacy of building in harmony with natural forces compels us to ask, what other profound secrets are still locked within the stones of the past, waiting to reshape our future? A gentle, continuous flow of water through a stone channel is a masterpiece of balance in motion. The ancient world's hydraulic engineers faced a paradox: how to command a fluid force that could not be commanded, only guided. Their solution was to build in perfect harmony with gravity itself. The Romans, in particular, transformed this principle into an art form. Their aqueducts snaked across the landscape, not in a straight plummet, but in a carefully calculated descent. The gradient had to be just right, a drop of perhaps only a few feet per mile. Too steep, and the water would rush forward, eroding the channel walls. Too shallow, and the flow would stagnate. Achieving this over dozens of miles, using only simple surveying tools like the predates, a precision leveling table, was a staggering feat of applied geometry. The Roman water commissioner Frontinus wrote with pride about this network, detailing the meticulous maintenance required to keep the lifeblood of the empire flowing. He understood that the system's longevity depended on its equilibrium, a constant, gentle pressure that never overwhelmed the stone and mortar. When these channels needed to cross a deep valley, the engineers displayed even greater ingenuity. They could construct a massive bridge of arches, like the magnificent Pont du Gard in France, its stacked tiers of stone carrying the water channel high above the river. Or, for a more direct route, they employed inverted siphons. This involved building a sealed pipe that would run down one side of the valley and up the other. The water, under its own pressure, would rush down and then climb up the opposite slope, a dramatic application of hydraulic principles that allowed them to avoid massive construction projects. But Roman ambition was not the only expression of this ancient water wisdom. In the arid landscapes of Persia, engineers developed the kanat, a gently sloping underground tunnel that tapped into groundwater far in the mountains and carried it for miles to the surface without a single pump. This was a sustainable system that prevented evaporation and brought life to the desert. Meanwhile, the Greek inventor Archimedes devised his famous water screw, a simple machine of a helix inside a cylinder that, when turned, could lift water from a river or ship's bilge with remarkable efficiency. What unites these diverse innovations from across the globe? They all represent a profound understanding of fluid dynamics, gained through observation and practice. These engineers did not fight the nature of water, they learned its language. They built structures that guided its flow, managed its pressure, and harnessed its energy, creating systems that sustained entire civilizations for centuries. This mastery over the most fluid of elements brings us to a final, haunting question. If they could achieve so much with so little, what foundational knowledge has been lost to the passage of time? The soaring vault of a Gothic cathedral does more than simply hold up the roof. Every flying buttress, a stone arm bracing the wall, performs a dual role. It channels the physical thrust of the vault away from the structure, while its upward reach embodies a spiritual yearning, a prayer in stone. This was the profound unity of ancient building, where symbolic meaning and structural logic were inseparable. Architects were not merely constructing shelters, they were composing a physical representation of the cosmos, and this cosmological vision directly shaped a building's stability. The Byzantine historian Procopius captured this feeling when he described the Hagia Sophia not as a building, but as a dome that seemed suspended from heaven by a golden chain. This was not just poetic exaggeration, it was a reflection of a core belief that a structure reflecting divine order would inherently possess divine endurance. This philosophy manifested in countless ways, grand columns were not just posts, they were stylized trees or even human figures, connecting the building to the living world and providing a psychological as well as physical foundation. The very floor plans were dictated by sacred geometry, circles and squares that represented the heavens and the earth. This use of perfect shapes was not arbitrary. It created a layout where forces were distributed with a natural, inherent harmony. The entire temple complex of Angkor Wat is the ultimate expression of this principle. Its vast moats and concentric galleries are a literal map of the Hindu universe, with the central towers representing Mount Meru, the axis of the world. This grand symbolic design demanded a structure of immense stability, and the builders achieved it through precise water management and massive, interlocking stonework. The complex was not just a depiction of a cosmic mountain, it was engineered to be one. Why would cultures across the globe share this conviction that spiritual harmony led to physical resilience? They perceived the universe as an interconnected whole, where balance in one realm reinforced balance in another. A design that resonated with cosmic principles was by its very nature a design in perfect equilibrium. This deep-seated belief compelled them to achieve a synthesis of mind and material, resulting in monuments that were as intellectually profound as they were physically unshakable. The submerged ruins of a Roman harbor still stand strong after 2,000 years, a silent rebuke to our own crumbling modern ports. This is the legacy of a lost material science, a concrete that did not merely resist the sea, but grew stronger within it. The secret was not in a single ingredient, but in a chemical reaction the Romans perfected, known today as the pozzolanic reaction. Their formula was deceptively simple, a mix of lime, volcanic ash from the region of Pozzuoli, and aggregate. When mixed with seawater, a remarkable transformation occurred. The lime and the reactive silica in the ash began to form a dense, interlocking network of crystals, a structure far more durable than the gel that forms in modern Portland cement. This crystalline matrix was the key to its immortality. Modern analysis has revealed an even more astonishing property: the presence of aluminous compounds. These minerals, reacting slowly over centuries with seawater, actually promote the formation of new minerals that fill any tiny cracks that form. This is a self-healing material, a technology we are only now beginning to engineer in laboratories. The Romans understood that one recipe was not enough for every task. They developed a range of mortars for specific purposes. A foundation might use a rigid, coarse mix for maximum compressive strength, while the joints between wall stones required a more flexible, lime-rich mortar that could absorb slight shifts without shattering. This nuanced understanding of material performance extended far beyond Rome. In ancient China, builders sometimes added organic materials like sticky rice soup or even animal blood to their mortars. These additives altered the mortar's working properties, creating a more plastic, workable mix that also trapped tiny air bubbles, potentially improving its resistance to freezing and thawing. The harbor at Caesarea Maritima is the ultimate proof of this ancient mastery. There, Roman engineers built massive concrete forms directly in the sea, creating breakwaters that have withstood the relentless Mediterranean waves for millennia. While our own concrete structures succumb to saltwater corrosion in decades, these ancient blocks have become harder with time. What does this mean for us today? It suggests that our path to a more durable future may not lie in inventing new, complex chemicals, but in rediscovering the elegant, time-tested alchemy of the past. This knowledge of materials was just one part of a larger system, a complete philosophy of building that integrated every element into a cohesive whole. The Great Pyramid of Giza stands as a perfect square on the landscape. its four sides aligned with the four cardinal directions with an error of less than 1/15 of a degree. This was no accidental achievement. For ancient builders, the heavens were not a distant mystery, but a living blueprint. They looked to the consistent, predictable movements of the stars and the sun to ground their most ambitious creations in cosmic order, believing that such alignment would bring their structures a share of the universe's own enduring stability. This celestial partnership was both a spiritual act and a profoundly practical one. Before a single stone was laid, the land had to be ceremonially prepared and oriented. In ancient Egypt, this began with the stretching of the cord ceremony. A priest and a goddess, represented by a ceremonial statue, would hold a cord between them. By sighting on the positions of specific stars, they would establish the sacred axis of the temple, literally laying the foundation stones along a line drawn from the sky. One of the most reliable methods for finding true north involved observing a single, unmoving point in the night sky. While our current North Star, Polaris, was not perfectly positioned in that era, Egyptian astronomers used the circular motion of other circumpolar stars around the celestial pole. By marking the points where a particular star rose and set, and then bisecting that angle, they could pinpoint north with astonishing accuracy. For the east-west axis, they used the sun. A simple vertical rod, known as a gnomon, was placed in level ground. The path of its shadow throughout the day was tracked, and the shortest shadow, which always points due north at solar noon, gave them their primary reference. This astronomical alignment served a clear functional purpose beyond the symbolic. At the Temple of Karnak, the entire main axis is oriented so that on the summer solstice, the rising sun would shine directly through the entrance, down the long hypostyle hall, and illuminate the inner sanctuary where the statue of the god Amun-Ra resided. This annual event transformed the architecture into a cosmic clock and a divine light show, reinforcing the pharaoh's connection to the gods. This principle of orienting structures to celestial events is a global phenomenon. On the Salisbury Plain, the heel stone at Stonehenge is positioned to frame the rising sun on the summer solstice, a moment that still draws thousands to witness its primal power. Across the Atlantic, the Pyramid of the Sun at Teotihuacan in Mexico is aligned so that its western face directly faces the setting sun on the same day. How did this celestial focus contribute to a building's actual permanence? A structure perfectly aligned with the forces of the cosmos was, in their view, in a state of perfect equilibrium. It was not fighting the universe but flowing with it. This careful orientation often resulted in layouts that maximized natural light and ventilation, regulating interior climates and preventing the moisture buildup that can erode stone from within. The ancient builders were not just constructing for their own time, they were calibrating their work to the timeless rhythm of the heavens themselves. The first stone columns of ancient Greece were not the graceful pillars we imagine today. They were heavy, squat, and spaced closely together, as if the builders were unsure of the very stone they stood upon. This was the Archaic period, a time of experimentation where the principles of balance were being learned not from theory, but from the hard lessons of structural failure. When an early temple wall settled unevenly or a roof collapsed, it was not seen as a disaster, but as a critical data point. Each crack taught them something new about load distribution, about the limits of their materials, and about the unseen forces they were battling. This process of trial and error was the true engine of their progress, a slow, meticulous accumulation of practical wisdom. The legendary lighthouse of Alexandria, one of the Seven Wonders, was not erected in a single, flawless campaign. Historical accounts suggest its construction spanned 12 long years, a period that would have been filled with constant problem-solving. Its designers were likely refining their plans even as the tower rose, adjusting the massive mirror assembly or reinforcing the interior ramp based on what they observed on the ground. This iterative design process was made possible by a master-apprentice system that preserved hard-won knowledge across generations. A young builder would not just learn how to carve stone, he would learn why a certain arch had failed 50 years prior and how to avoid that same mistake. Before committing to a monumental project, they would often test new ideas on a smaller, less critical structure, a sacred gateway or a treasury building, proving the concept before scaling it up. We can see this learning process etched in stone at the Heraeon on the island of Samos. The temple was rebuilt multiple times over the centuries, and with each new phase, the design improved. Later versions featured more slender columns set farther apart, a clear sign that engineers had grown more confident in their understanding of the stone's strength and the mathematics of support. This confidence was fueled by parallel innovations in the builder's toolkit. The invention of more efficient cranes and capstans powered by human treadmills allowed them to lift heavier stones with greater control. Simultaneously, the development of sophisticated wooden scaffolding gave workers safe access to dizzying heights, enabling the precise placement that these evolving designs demanded. What does this long, patient journey toward perfection reveal about true innovation? It shows that ancient mastery was not a sudden flash of genius, but the quiet, persistent result of learning from every setback. They understood that progress was built not just on success, but on a foundation of carefully studied failures. A single trade route did more than carry silk and spices, it transported entire schools of thought. The Silk Road was a conduit for the science of balance itself, a sprawling network where architectural secrets were among the most precious commodities. The flow of ideas between Persia, India, China, and the Mediterranean was constant and transformative. This was not a simple matter of copying, but of creative adaptation. A brilliant idea would travel thousands of miles, and upon arrival, local builders would reinterpret it using the materials and aesthetic traditions they knew best. The pointed arch, so iconic in the soaring Gothic cathedrals of Europe, did not originate there. Its elegant, gravity-defying form was perfected centuries earlier in Islamic architecture, visible in structures like the Alhambra in Spain. This was not a coincidence, but evidence of a profound cross-pollination. Scholars and master craftsmen were the vessels of this knowledge. The travels of figures like Marco Polo were not just journeys of exploration. They were missions of technical exchange, where a builder might share the secret of a new mortar recipe or a more stable vault design with a community an entire continent away. Consider the dome. This architectural marvel was refined by the Romans, embraced and transformed by the Byzantine Empire with breathtaking complexity in the Hagia Sophia, and then carried eastward, where it was reimagined in the grand mosques of the Islamic world. In each new location, the dome was modified. Its curvature might become more pronounced, its supporting walls thicker or more ornate, all to accommodate local seismic conditions or the properties of regional stone. This global conversation accelerated innovation at an incredible pace. The influence of the Indian stupa, a solid, mound-like structure housing relics, traveled across Southeast Asia. As it spread, its form evolved into the towering, elaborate temples of places like Angkor Wat, where the basic concept was scaled to a monumental level and integrated with intricate water management systems. Similarly, the engineering prowess of the Roman Empire did not vanish with its fall. It was preserved, studied, and advanced by the Byzantine and then the Ottoman empires, who incorporated Roman aqueduct technology and mortar science into their own magnificent mosques and palaces. Even in West Africa, far from the Mediterranean heartland, we see a unique expression of this shared human ingenuity. the Great Mosque of Janeh in Mali, built from sun-baked adobe bricks, showcases a distinct Sudano-Sahelian style. Its massive walls are studded with protruding wooden timbers that are not merely decorative. They serve as permanent scaffolding for the regular replastering required by the seasonal rains, and they create a textured surface that casts dramatic shadows, strengthening the entire structure against cracking in the harsh sun. How did this constant cultural crosstalk change the ancient world? It created a shared pool of knowledge, a global brain trust where a breakthrough in one civilization could become a foundational principle in another. The entire ancient world was, in effect, collaborating, pushing the boundaries of what was possible with stone and mortar. This legacy of shared innovation compels us to look back and wonder what other forgotten connections lie hidden in the stones of our most cherished monuments. Inside a traditional Japanese temple, the air is scented with ancient cypress. Overhead, a complex lattice of wooden beams interlock in a silent, gravity-defying dance. This is the art of joinery, a system so precise it forgoes nails and screws entirely, relying instead on the perfect marriage of carved wood. Each joint is a calculated puzzle piece, designed to accommodate the wood's natural desire to breathe, shrink, and move with the seasons. A master carpenter does not simply cut wood. He reads its grain, understanding its strengths and anticipating its future shifts. This knowledge was codified in texts like the Chinese Lu Ban Jing, a carpenter's manual detailing hundreds of distinct joints for every conceivable purpose. It presents a philosophy where the connection itself is the source of strength. The fundamental principle is simple yet profound: the mortise and tenon. A protruding tenon on one beam is fitted snugly into a carved cavity, the mortise on another. This creates a locked connection that can bear immense weight. But the true genius emerges in more complex forms like the dovetail, with its flaring, trapezoidal shape that resists being pulled apart, and the intricate Japanese kigumi, where beams are notched and interwoven in 3 dimensions, creating frameworks that are as much art as architecture. These joints are not rigid locks. They are designed with a subtle intelligence, allowing the entire structure to flex and sway, absorbing the energy of wind and earthquake. The strategic placement of every joint is critical, always positioned away from points of highest stress to prevent splitting. At Japan's Horyu-ji Temple, one of the oldest wooden buildings on Earth, this philosophy is alive in every beam. Its pagoda stands not because of sheer mass, but because of the countless perfectly fitted joints that allow it to dance with seismic forces, dissipating energy through its flexible skeleton. The carpenters even used entire tree trunks as columns, orienting them so the wood's natural curvature countered the building's load, a perfect synergy between material and design. What is the secret to its millennium of endurance? It is a strength born from connection and flexibility, a reminder that resilience often lies not in rigid resistance, but in the intelligent give and take of interlocking parts. A single, weathered stone rests off-center in a sea of raked gravel. Its placement feels instinctively correct, yet it defies every rule of perfect symmetry. This is the heart of a Japanese rock garden, a physical expression of the philosophy known as wabi-sabi. This was not a mere artistic style. It was a profound architectural principle that understood true stability emerges from embracing the irregular, the imperfect, and the transient. Where Western traditions often sought to conquer nature with geometric perfection, wabi-sabi invited the natural world into the very soul of a structure. It accepted that wood warps, stone weathers, and that a building is a living entity in constant dialogue with its environment. The tea master Sen no Rikyu elevated this aesthetic into a spiritual practice. He championed the beauty of rustic, unadorned materials, like a clay tea bowl with an accidental glazed drip or a timber post that still showed the mark of the adze. This was not a celebration of carelessness, but a deep appreciation for inherent strength and authenticity. An object that accepted its own nature with all its so-called flaws possessed a resilience that a perfect, brittle copy could never achieve. How did this philosophical acceptance of imperfection translate into tangible structural integrity? It began with the choice of materials. Builders would select timber for its natural curves and knots, using each piece for the specific structural role its unique shape was best suited to perform. A gently bowed beam might be placed in a position where its curve would naturally counteract a future load, turning a perceived weakness into a source of strength. They used uneven stones in foundations, carefully fitting them together in a way that created a dynamic, interlocking mass far more resistant to shifting ground than a rigid grid of identical blocks. At the Katsura Imperial Villa in Kyoto, this philosophy is woven into every corridor and garden view. The building appears to have grown organically from the landscape. Floors gently slope, posts are intentionally irregular, and the lines between the interior and the exterior blur completely. This was not haphazard construction, it was a masterclass in dynamic balance. The entire structure is designed to accept and absorb movement, from the seasonal swelling of the wood to the subtle settling of the earth. Perhaps the most radical idea was the intentional incorporation of weathering. The silver-gray patina of aged cedar or the soft green moss on a stone lantern were not signs of decay to be fought, but were considered the final, beautiful layer of the design. The building was not meant to defy time, but to age gracefully with it, its beauty and its strength evolving together. Why would a culture choose to build with such deliberate asymmetry? Because they recognize that nature itself is never perfectly symmetrical. A structure that mirrors the irregular balance of a forest or a mountain stream achieves a deeper, more authentic form of equilibrium. It becomes part of the landscape rather than an imposition upon it. This profound acceptance of natural forces created a resilience that was not just physical, but deeply philosophical. A whisper can travel the entire length of Gol Gumbaz's vast chamber, a secret passed from one wall to another with perfect clarity. This whispering gallery effect is no architectural accident. It is the signature of a lost science where builders engineered not just for the eye but for the ear. In sacred spaces across the ancient world, sound was a material to be shaped and directed, as vital to the structure's purpose as its foundation. These architects understood that the voice of a priest, the chant of a chorus, or the strum of a lyre was an invisible force that could be amplified, focused, or softened through the geometry of stone. They designed domes and vaults to act as natural sound mirrors. A perfectly curved surface, like the inside of a parabola, can catch a sound wave and reflect it to a single, distant point, creating an acoustic hotspot where a speaker's words would land with uncanny force. Conversely, they knew that rough, textured walls or strategically placed columns and niches would break up sound waves, scattering them to prevent jarring echoes and create a more diffuse, immersive atmosphere. The Roman writer Vitruvius left explicit instructions for this sonic art. He detailed how to place bronze vases in the cavities of theater walls, tuned to specific resonant frequencies to amplify the actors' voices and enrich the music. This was an early form of acoustic resonance, using the vibrations of the metal to reinforce the vibrations of the air. The choice of material was equally critical. Polished marble and smooth plaster, which reflect sound brilliantly, were used to carry sound over long distances, while porous stone and timber could absorb excess reverberation, preventing a sacred chant from dissolving into a muddy cacophony. The ultimate testament to this ancient mastery is the theatre of Epidaurus in Greece. Its semicircular orchestra and steeply banked stone seats are an acoustic miracle. Without any electronic aid, a performer's quiet word, or even the soft clink of a coin dropped on the stage, can be heard with perfect intelligibility in the very last row, nearly 200 feet away. The secret lies in the precise step design of the seating, which acts as a filter, scattering low-frequency crowd noise while perfectly reflecting the higher frequencies of the human voice up to the top tiers. Why did these cultures invest such profound effort into the control of sound? Because they understood that architecture was an experience, the power of a ritual, the drama of a play, or the authority of an orator depended on being heard. A message that was lost in echoes or drowned by noise was a message that failed. By weaving acoustic perfection into the very fabric of their buildings, they added an invisible yet deeply felt dimension to structural perfection. This mastery over the physical environment reveals a final, haunting layer of their genius, one that connects the built world directly to the human spirit. The Great Wall of China snakes across mountains for thousands of miles, a project so vast it consumed the labor of millions across multiple dynasties. This was more than a wall, it was the ultimate expression of ancient project management, a logistical puzzle that makes even our modern mega-projects seem modest. The true wonder lies not in the stone and mortar, but in the invisible systems of organization that made it possible. These were immense economic and social engines, fueled by a sophisticated understanding of supply chains and human resource management. In ancient Egypt, papyrus records from Deir el-Medina reveal a highly structured workforce living in a purpose-built village. Quarrymen, carvers, water carriers, and scribes all played a specialized role, their work coordinated with the precision of a military campaign. Scribes meticulously recorded daily rations of grain, fish, and beer, ensuring the workforce was fed, paid, and motivated. This was not slavery in the simple sense, but a complex system of conscripted labor where workers served in rotating shifts, often as a form of tax obligation to the state. Funding for such endeavors flowed from the royal treasury, filled by taxes on grain, trade, and tribute from conquered lands. Every block of stone had a cost that was carefully tracked from quarry to construction site. To manage projects of such scale, ancient administrators developed standardized measurements. The royal cubit in Egypt and the Roman foot provided a consistent unit across the entire empire, allowing plans drawn up in the capital to be executed with perfect accuracy by builders 1,000 miles away. This standardization was the bedrock of logistics. The Roman road network itself was a logistical miracle, a web of stone highways that enabled the movement of legionaries, but also of countless cartloads of marble, timber, and tile. These roads were the supply lines that built an empire, allowing materials from specialized quarries to reach distant cities. At the peak of a project, temporary worker cities would spring up near the construction site, complete with bakeries, infirmaries, and administrative offices, becoming bustling hubs of activity that vanished once the final stone was laid. What can a modern project manager learn from these ancient enterprises? They teach us that the greatest physical structures are born from an even greater mastery of information, coordination, and the meticulous care of the human effort behind them. The rose-red city of Petra does not stand on the desert landscape, it emerges from within it. This is the ultimate expression of building with the land, a philosophy where the natural topography was not an obstacle to overcome, but the primary partner in creation. The Nabatean builders did not quarry stone to then assemble into walls. They carved their temples and tombs directly into the living rock of the cliff faces. This approach provided an immediate and profound structural advantage. using the mountain itself as both an unshakable foundation and the primary building material. The solid bedrock eliminated any risk of settling or shifting that could fracture a freestanding structure. The cliff walls became load-bearing elements of unimaginable strength, offering natural shelter from the harsh desert sun and fierce winds, while also providing a form of camouflage, making the city a hidden fortress. This deep integration extended far beyond the grand facades. The Nabateans were masters of hydrology in an arid land. They engineered a complex system of channels, dams, and cisterns that captured every precious drop of seasonal rainwater, directing the runoff away from their delicate structures and into storage for the dry months. They sited their buildings with meticulous care, always seeking the solid embrace of bedrock to anchor their work. A hillside was not flattened. It was transformed into a series of terraces that prevented erosion and created level platforms for daily life. Natural caves and recesses were incorporated into designs, their stable, cool interiors offering natural temperature regulation long before the invention of modern insulation. This same principle of seamless integration is echoed halfway across the world in the cliff dwellings of Mesa Verde. There, the ancestral Pueblones built entire villages beneath massive sandstone overhangs. The cliffs provided a giant protective roof, shielding the communities from snow and rain, while the natural rock walls formed the backbone of their multi-story homes. The orientation of these dwellings was carefully calculated to maximize the low winter sun for warmth, while the deep overhangs provided shade during the intense summer heat. How does this deep integration contribute to both longevity and aesthetic power? A structure that grows from its site achieves a form of permanence that feels both ancient and inevitable. The forces that destroy buildings, water, wind, and shifting ground are not fought against but are managed and channeled by the design itself. The aesthetic power is equally profound. These places possess a haunting beauty because they feel intrinsically right, as if they were always meant to be there. The builders did not impose their will upon the earth. They listened to its form and allowed the landscape to guide their hands, creating a legacy of resilience that is written not just in stone, but in the very shape of the land. A deep chant reverberates across a high mountain plateau, its rhythm matched by the slow, deliberate beat of a massive drum. According to legends preserved by Tibetan monks, this was not ceremony alone, but the very method of construction, a means of making colossal stones light enough to be guided into place by human hands. Similar stories echo from the builders of the Great Pyramid, who supposedly moved stone blocks by striking them with rods, and from indigenous traditions in the Americas that speak of making rocks lose their weight through song. These accounts form one of the most tantalizing enigmas in ancient history, the idea that sound itself was a tool for construction. Mainstream archaeology rightly points to the overwhelming evidence for ramps, levers, and immense coordinated labor. Yet the sheer scale of certain achievements, like the placement of the 800-ton Baalbek stones in Lebanon, continues to inspire questions about whether we are missing a piece of the puzzle. Could there be a kernel of truth buried within these ancient legends? Modern science offers a fascinating, though limited, parallel in the form of acoustic levitation. In laboratories today, scientists use precise sound waves to suspend tiny droplets of water or plastic beads in mid-air. The physics is real. A carefully tuned frequency creates a standing wave with nodes, points where the acoustic pressure can counteract the force of gravity. The energy required to achieve this, however, scales dramatically with the size and mass of the object. To levitate a stone weighing even a single ton would demand a sound source of unimaginable power, far beyond any drum or trumpet we know of from the ancient world. A more plausible application lies not in full levitation, but in the manipulation of friction. every object has a natural resonant frequency, a specific pitch at which it vibrates most easily. If a large stone block were subjected to a powerful, rhythmic beat at or near this frequency, the resulting vibrations could theoretically reduce the friction between the stone and the ground. This would not make the stone weightless, but it could make it significantly easier for a team of workers to slide it along a track or a sledge. The rhythmic labor chants recorded across countless cultures may have served a dual purpose, not only coordinating the immense physical effort, but also introducing a steady vibrational energy into the task. The legends themselves are a form of cultural memory, a way of encoding a profound truth about the construction process. The use of trumpets and drums at a temple site was undoubtedly a sacred act, a way of sanctifying the space and aligning the work with spiritual forces. In a world where science and spirituality were not separate, the powerful, coordinated sound that helped hundreds of workers pull in unison would have been perceived as a magical force, a vibration that moved both stone and spirit. So were ancient builders using a lost science of sonic engineering. The evidence for large-scale acoustic levitation remains in the realm of compelling speculation. But these persistent legends challenge us to expand our understanding. They suggest that ancient masters may have been harnessing the physics of their environment in ways we are only beginning to appreciate, using every tool at their disposal, from the strength of their bodies to the resonant power of their collective voice, to achieve the impossible. The clear, life-giving water that once flowed through Roman aqueducts slowed to a trickle and then fell silent. With the empire's political collapse, the intricate knowledge required to maintain these engineering marvels began to fade from memory. It was not a single catastrophic event that erased these arts, but a slow, grinding decay. The historian Edward Gibbon observed this decline of technical skill as a defining feature of the era, a time when the very formulas for Roman concrete, a self-healing material that had defied the sea for centuries, were misplaced for over 1,000 years. This loss reveals a profound truth about human progress. It is not a constant upward climb, but a fragile inheritance that can be broken. The disintegration of vast, centralized states like Rome shattered the complex systems that preserved advanced knowledge. Guilds and master-apprentice chains, which had meticulously passed down precise geometric rules and mortar recipes from one generation to the next, were disrupted by widespread social upheaval and conflict. The focus of building shifted dramatically from grand civic projects to immediate survival, leading to the construction of smaller, more defensive structures like fortified keeps and walled towns. In this new world, the mathematical and astronomical precision that had aligned temples with the stars was no longer a priority, replaced by a more pragmatic, though less enduring, approach to construction. A poignant symbol of this decline is the dome of the Hagia Sophia itself. After a severe earthquake in the year 558 damaged the original structure, the engineers tasked with its repair lacked the full understanding of their predecessors. They were forced to rebuild the dome higher and with heavier materials, a solution that lacked the elegant equilibrium of the original design and made it more vulnerable in the long term. What does this collective amnesia teach us? Our technological achievements are not permanent possessions. They are a living tradition dependent on stable societies, dedicated institutions, and the continuous, careful passage of wisdom from one hand to the next. The disappearance of these arts created a void in our understanding, a puzzle we are still piecing together today, reminding us that the greatest structures we build are not of stone, but of knowledge itself. A laser scanner paints the Colosseum with an invisible grid of light, capturing every fracture and contour with sub-millimeter precision. This is not just digital preservation, it is a technological autopsy, allowing modern engineers to peer through time and witness the structural genius at work. Inside a computer model, a simulation known as finite element analysis subjects the ancient amphitheater to virtual earthquakes and immense crowd loads. The results are a revelation. The complex network of arches and vaults, long admired for their beauty, is exposed as a masterfully engineered system for channeling stress. The analysis shows that the weight of 50,000 spectators is not merely supported, it is elegantly guided along predetermined paths, flowing through the stone like water through a riverbed, avoiding any single point of failure. This hidden intelligence is now being decoded across the ancient world. Ground-penetrating radar unveils the deep, stratified foundations of Mayan temples without moving a single stone. Drone photography, stitching together thousands of high-resolution images, creates three-dimensional maps of sprawling sites like Angkor Wat, revealing alignments and hydraulic systems invisible from the ground. The scientific validation of ancient mastery often yields profound surprises. At the Massachusetts Institute of Technology, a team has successfully recreated the legendary Roman concrete. Their experiments confirmed the long-held theory: the incorporation of volcanic ash creates a material that, when cracked, allows moisture to seep in and react with the lime, forming new crystals that seamlessly fill the gaps. This self-healing capability, a technology we are still struggling to perfect, was a commonplace recipe 2,000 years ago. Similarly, stress analysis of Gothic cathedrals shows that their iconic flying buttresses do more than brace the walls. They create a perfect equilibrium, transforming the crushing weight of the vault into a graceful, outward thrust that is then captured and neutralized. Even the Leaning Tower of Pisa, a monument to a foundational miscalculation, has become a priceless case study. Centuries of monitoring its slow tilt have provided invaluable data on soil structure interaction, principles that now inform the construction of skyscrapers on unstable ground. What new old principles are we uncovering through this scientific lens? The study of ancient mortars, often made with locally sourced natural materials, is inspiring the development of eco-friendly, low-carbon alternatives to modern cement. These tools are not just revealing the past, they are giving a second life to ancient wisdom, proving that the builders of old possessed a holistic understanding of their materials and environment that we are only now, with all our technology, beginning to fully appreciate. A future skyscraper might not rely on steel beams, but on a massive, interlocking stone puzzle, each block designed to be taken apart and reassembled like a set of giant Legos. This vision, drawn directly from Incan walls, points toward a radical shift in how we build. The ancient science of balance offers a direct blueprint for tackling our modern crises of waste, energy, and a changing climate. These builders were the original masters of sustainability, working exclusively with local, low-energy materials and designing for centuries, not decades. The architect Christopher Alexander called for a return to such timeless principles, patterns that create spaces which feel truly alive and rooted in their place. So what are the key lessons we can reclaim? First is the principle of designing for disassembly. Instead of welding and gluing buildings together into permanent, toxic tombs, we can create structures with intelligent joints that allow materials to be recovered and reused indefinitely, creating a circular economy of stone, wood, and earth. Second is the mastery of passive environmental control. Ancient builders used thermal mass, the inherent ability of dense materials like stone and earth to absorb heat during the day and release it slowly at night, to naturally regulate interior temperatures without any electrical input. This leads directly to the third lesson, prioritizing durability over cheap speed. A structure that stands for 1,000 years, like the Roman Pantheon, has a far smaller environmental footprint over its life than a modern building that must be demolished and rebuilt every 50. The final and perhaps most profound takeaway is the seamless integration of buildings with their ecosystems. Ancient cities were not imposed upon the landscape. They were grown from it, working with the natural drainage, sun paths, and wind patterns. One of the most promising ancient techniques seeing a modern revival is rammed earth construction. Walls are formed by compacting layers of damp earth, often stabilized with a small amount of lime, into sturdy, monolithic forms. These walls are not only incredibly strong and fireproof, but they actively pull carbon dioxide from the atmosphere as the lime cures, turning a building into a tool for carbon sequestration. We see this ancient logic reborn in projects like the Eastgate Center in Harare. Its design mimics the self-cooling tunnels of a termite mound, using a combination of thermal mass and clever chimney effects to maintain comfortable temperatures while using 90% less energy for air conditioning than conventional buildings of its size. This is biomimicry, but it is also a rediscovery of a very old idea that the most efficient systems are those that work with nature, not against it. The question for our time is how to weave this deep, place-based wisdom together with our powerful new technologies. The answer may lie not in inventing a completely new future, but in recovering a forgotten balance, creating a built environment that is both resilient and inherently harmonious. Massive stone blocks at Mycenae were so immense that later Greeks believed only one-eyed giants, the Cyclopes, could have lifted them. This was not a dismissal of human ability, but a form of awe so profound it required a mythical explanation. When faced with a wall of stones weighing 50 tons each, the alternative seemed impossible, that ordinary people had achieved such a feat through knowledge and coordination alone. The legend served a deeper purpose than mere storytelling. By attributing the construction to the Cyclopes, the Mycenaeans embedded their citadel within a divine narrative, elevating its status from a mere fortress to a place touched by primordial power. This pattern repeats across cultures and epochs. The biblical Tower of Babel stands as a powerful symbol of this same impulse, a story where humanity's collective ambition to build a structure reaching the heavens is met with divine intervention. The narrative captures a universal tension, the thin line between monumental achievement and perceived hubris, suggesting that some constructions felt so grand they challenged the very order of the world. In Ireland, the spectacular basalt columns of the Giant's Causeway were explained through the legend of the giant Finn McCool, who supposedly built it as a stepping stone path to confront a rival in Scotland. The natural geological formation was so perfectly geometric that it demanded a supernatural architect. Similarly, the majestic temples of Angkor were not seen as mere human creations by the Khmer people, but as the abodes of gods, their construction often ascribed to divine mandate or celestial architects. This blurring of technical skill and divine intervention was a powerful tool. It transformed a king into a god-king and a building into a sacred monument, ensuring its protection and significance for generations. Even today, this psychological impulse persists in theories that credit the pyramids of Giza to a lost civilization or extraterrestrial visitors, a modern myth born from the same reluctance to accept the full scope of human ingenuity. Why does our mind so readily reach for the supernatural when confronted with incredible achievement? These enduring legends remind us that the most powerful constructions have always served a dual purpose. They were not just physical shelters or fortifications. They were vessels for belief, physical anchors for a culture's deepest values and its understanding of its place in the cosmos. The stone itself was only half the structure, the other half was the story woven around it, a story that granted it a life far beyond its mortar and blocks. Our journey through the quarries and temples of the past reveals a universal blueprint for building. It is a language spoken in the perfect fit of Incan stones, the graceful curve of a Roman arch, and the sway of a Japanese pagoda. This language is built on a deep respect for natural forces, a patient process of learning from failure, and a profound integration of form, function, and belief. The result is a legacy of structural perfection that has endured for millennia, monuments that stand as a quiet challenge to our modern assumptions about progress and permanence. The philosopher George Santayana offered a timeless warning, reminding us that those who cannot remember the past are condemned to repeat its mistakes. His words urge us to look back, not in nostalgia, but for inspiration. What if the path to a more resilient and sustainable future is not found in the next new material, but in the recovered wisdom of the first builders? Let this exploration be a call to re-examine the knowledge locked within these ancient stones. Let us consider how we might weave these timeless principles of balance, proportion, and material intelligence into the fabric of our own cities and homes. We would love to hear from you. Which ancient structure captures your imagination the most? Share your thoughts in the comments below. If you enjoyed this journey into the mysteries of our shared past, subscribe for more. And as you go, remember to seek balance in all that you build.